Hello. This is the second part of the algorithms where we're looking at recursion. So the idea of recursive computing. This is part 2, as I already said, and now we're going to see how to analyze recursive computing in terms of mathematical descriptions. A recurrence for a function f of n defined on the integers is an equation that expresses that function f of n, or the value of f of n, recursively in terms of the values of f of k, where k is smaller than n. So this is again the same idea of that we saw in the previous video of having expressing a larger problem in terms of smaller problems, and this is actually a mathematical function. So one of the most famous recurrences is given by the Fibonacci numbers. Leonardo Bonacci, known also as Fibonacci, was an Italian mathematician, and he is considered by some like the most talented Western mathematician of the Middle Ages. Importantly, Fibonacci is best known in the modern world because he spread the Hindu-Arabic numeral system in Europe. He went traveling, and he learned a lot from both in Sanskrit, reading the Sanskrit, and also in Arabic. He didn't actually invent what we know today as the Fibonacci numbers. He discovered the Fibonacci numbers used in Sanskrit to create poems. So these numbers were used as a sequence for creating poems. And when he brought it back to the Western part of what was known then as the Western part of the world, he wanted to explain that to the people in Europe. And the way to explain it to them, he came up with a story. And the story is the following. Take a pair of rabbits that mature in 1 month. When a pair is mature, it then produces a new pair each month. Each new pair takes a month to mature before they can have pairs of babies of their own. And the question is, after n months, how many rabbits are there? And of course, in here, we're going to assume that there are no deaths of rabbits or anything. We just see how that would grow. And that's the problem that the way that he explained these numbers. So how do we write this in a mathematical way? How do we use mathematics to express the sequence, to express the evolution of the number of rabbits at each of the generations? So F is going to be the number of rabbits, the number of pairs, and N is going to be the month. Now, we realized that the number of pairs of rabbits in the previous month is comprised of pairs of baby rabbits and pairs of mature rabbits. How can we actually know which are which? Well, this expression above is telling us take the total number of pairs in generation n-1 and subtract the one from the previous generation. So the leftover is the new rabbits. It's just the ones that are exceeding in the new generation. So these are necessarily the ones that were born at that n-1 generation. So these are the pairs of baby rabbits. And of course, in order to express f of n-1 equals this plus the number of mature rabbits, we have to add this number, because now, of course, we need to realize that this number and this number will cancel each other in the sum. So when we add this plus this cancel, and we obtain fn-1 equals fn-1. So breaking up that, that's a logic to breaking up that way. Then we're ready to find what is the recurrence, the mathematical recurrence, because we know the rules. The rules are the following. the pairs of mature rabbits double in each month. So that's what we know. The pairs of mature rabbits, which is the one here below, are going to double for the following time. So at the generation n-1, the number of pairs of mature rabbits is fn-2, and this is why we have to multiply by 2. So in generation n, all of the pairs of mature rabbits are going to double. But the pairs of baby rabbits just stay the same way. So they are not going to die in this particular model, but they're not going to reproduce because they're not mature yet for reproducing. So the pairs of baby rabbits only come in this second way. So that's the way that we can write the number of pairs of rabbits in month n as a function of the number of pairs of rabbits in generations n-2 and n-1, obtaining the very well-known, and I suppose that most of my audience would recognize, the very well-known recurrence for the Fibonacci numbers. You start out with a 1 and a 1, and then you start adding up the 2 previous numbers in order to get the following in the sequence. So this is the recurrence that describes the Fibonacci numbers. So in this video, I am going to suggest some exercises for you. You can pause the video, do it at your own time. You know, there's something like this kind of thing. It's called a notebook. And this is the kind of thing that we used to use a long time ago. And this is called a pen. And you can actually use that to write your own exercises and your scribbles, and it actually helps a lot to understand not just programming directly on the computer, but sometimes it actually helps if you try to do that. So in this exercise, I came up with this idea that everybody knows about paying the mortgage, and you know, everybody knows that you're paying a monthly amount that I'm calling here capital M. So those are your monthly payments. Now, the initial amount that you put as a down payment, I call it capital A. And we all know that, you know, when you write a contract for a mortgage, they give you an interest rate. And the interest rate is expressed in terms of R%, which is an annual percent. So I'm dividing the percent by 12 because we want to know month by month. We want to know what is the amount of the debt that remains. And it will depend on the amount of the debt that you had the previous month. So the exercise for you is think about this. How would you write the recurrence for the amount of debt that you still have in your contract at month end? Now, what is the relationship between the recurrence and, you know, the recursive computation? So the cost is defined, the computational cost or running cost is defined in terms of the CPU time that it takes to run the algorithm. And it is assuming that each of the basic operations, like addition or writing into a file or reading from a file and so on, addition, subtraction, things like each of the basic operations takes a fixed amount of time. And if you know your compiler, you probably also know how much that is for each of the basic operations. So we normally, in theory, calculate the total cost of the algorithm by counting the number of basic operations. So we simplify a little bit the problem and we do that. Now, I actually wrote this in gray because the actual running time is a lot more complex today than just counting the number of iterations. Way back when I started programming, computers were doing things in sequence, serial computers. But now we have parallel cores. We have computers connected to the internet. There are a lot of different processes that are going on that we don't even know about. that might have to do with the apps that you have installed. And so the running time might actually be different from one day to the next. And if you're using the internet or cloud computing, it can be more complicated. But we're not going to get into that. Right now, we're basically just considering that the cost is the number of basic operations. In my previous video, when I was talking about subcontracting to illustrate the notion of recursive computation, I was saying that moving a disk was in the towers of Hanoi was going to cost $1. And then I said, well, writing the number in the array for the merge procedure is also going to cost $1. And if we know, if we give an idea of a cost like that, it's easier for us sometimes to understand how do we evaluate the computational cost. In computer science, it is often, the recursive algorithms are often referred to as divide and conquer algorithms because the idea is to divide the problem into smaller problems, and by doing that division, we conquer the solution. So that's why they're called divide and conquer. So let me write the recurrence for the towers of Hanoi. And of course, I'm referring to my previous video where we explained all this picture. The idea is the following. At the step n, the cost T of n will be the total cost incurred. So basically, I am calling the subcontractor to move n-1 towers. So I was calling Nina, Nina was calling Jamal, and Jamal was calling Pedro. But each one of us was doing basically the same structural thing. We were calling the subcontractor for n-1, and so we're going to have to pay that subcontractor T of n-1. Then we move one disk, which is the $1. And then we call the subcontractor again, which is depicted in the last part of the figure, to finally move the whole tower. So what this means is that in the particular case of the towers of Hanoi, the mathematical recurrence is explained in this particular way. So Tn is equal to twice Tn-1 plus 1, and we have what we call the base case, or the initial condition, which is T1 equals 1. And so that's the way that we describe the cost. Going further, the other example that we saw was the merge sort. And in the merge sort, we are dividing each of the steps. We're dividing in half an array in one side, half an array in the other. Now, for simplicity, although this is not necessary, I am going to assume that the total number of elements that we want to sort in the original big array is a power of 2, so that we can always divide by 2 and always get integers. It's just for convenience, although this is not really necessary for the analysis of the algorithm. So if we assume that, then what we were doing again with the subcontracting was that we were asking someone else to solve 2 problems that each of them were half the size of the original problem. And that's why we have a 2 here in front, because the subcontractor has to do 2 of the problems. And then once the subcontractor does the sub-problems, the 2 of them, then we have to merge the lists. And as we saw in the previous video, merging is linear cost in n. So this is where I'm writing here as C times, is a constant C times n. So this is the recurrence that describes the merge sort, the cost of the merge sort algorithm. Now, as an exercise for you again, I'm going to ask you to think about this. Take your favorite notebook and your pen if you want, I sometimes write on my windows. That's kind of nice. So this exercise is about something called binary search, which is one of the most popular algorithms. And if you are in computer science, you probably know everything about binary search. It's very, very well known. So the idea is the following. The mission that you have to accomplish is the following. You have an array, and this is an array of integers, and there is a target value alpha. You have to find the index I star such that the array, the element, the I star element in that array is equal to alpha. Now, because the array A is already ordered, then you basically have to do a search for that number. So the homework that I have for you, the exercise that I'm suggesting that you do is to write the recursive pseudocode for this problem and find the recurrence that describes the running time. You're going to have to look at, you're probably going to have to look at the previous examples, or, as many people do, you Google it and you try to find if someone else has done something like this. But it's a good thing to think about it. Now, I just added in this slides a motivation for this type of binary search. For example, this is actually called route finding or target tracking in general. Let's suppose that you have a heater and the indices in the array are labeling the settings on a heater. So setting 1, 2, 3, 4, 5, and they are going farther and farther away. Now, this heater could be actually on your stove or something. And you want to achieve a setting that will produce a very particular desired temperature alpha. So what you need to do is to find that particular index. So that's a motivation for the kind of problem that we have. Of course, now we do everything with intelligent computers. So we would like to be able to program a computer that very quickly is capable of finding the index I star, the optimal index. Now, in the more general setting, these numbers don't need to be integer valued, so they could be real valued, and it's not necessary to assume that the actual target alpha is contained in the array. In that case, we replace in the goal, we replace the less or equal sign with a strictly less sign. Well, that's basically what we would do if the number doesn't appear. We basically just find the best index in the array that will fit the target alpha. So that's an exercise for you. Just pause the video, try to do it. So are we done yet? So that's it. We've seen how to use recurrences in order to describe the computational cost. So I went back and I realized that I have the invoice from the team, basically Nina and her team that solved the towers of Hanoi for me. So I went on and I wrote the check. This check is correct. It contains all the information that you actually need. It says the base case in the memo, and it has the recurrence. However, I doubt very much that the bank is going to deposit this check. So this is actually not enough. Next time, we'll see how do we solve the recurrences. Thank you for watching.